Gauss law for magnetic field. We have previously studied Gauss law for electric field, and in Gauss law for electric field we said that if we have a closed surface enclosing a charge, so the integration over this closed surface of the electric field equals the value of this charge included inside the surface over epsilon naught. Now we have something similar in magnetic field, but in the case of the magnetic field, the simplest magnet, it can be represented with two poles, north and south, which is equivalent in electric charge, positive and negative. So the magnet with its two poles is an example of magnetic dipole. So the simplest magnetic structure that can exist is a magnetic dipole. For example, if we have a magnet bar with north and south, and we divide this magnet bar into smaller pieces, we find out all these smaller pieces are consisting of north and south, north and south, north and south, and so on. So we cannot extract the north separately from the south. So any magnet in the world include both north and south in its poles. So there is no one pole, there is no one charge of magnetic charge in magnetic fields. So that's what we're saying. The simplest magnetic structure that can exist is a magnetic dipole. Magnetic monopoles don't exist. We cannot find north only or south only. Gauss law for the magnetic field is a formal way for saying that magnetic monopole don't exist. How comes? In the electric field, Gauss law states that the integration of the electric field over a closed surface equal the charge inside this surface over epsilon naught. So if you are going to say the same for the magnetic field, we will say the integration of the magnetic field over a closed surface would equal the magnetic charge inside this surface. And because there is no magnetic charge, there is no monopole, so this integration over a closed surface is always zero. So Gauss law for magnetic field is a formal way for saying that the magnetic monopole don't exist. The law asserts that the net magnetic flux phi b through any closed surface, any closed Gaussian surface, is zero. How comes? Assume that we have, for example, this is a closed surface around the North Pole. We will find that these lines of magnetic flux is going out from the surface. But these lines is turning back to be inside from the bottom surface. So the number of lines going out of the surface equals exactly the number of lines enter the surface. So this is the surface around the North Pole. If the surface is away from the North or the South Pole, for example this surface, we can find the number of lines enter the surface equals the number of lines out the surface. So regardless where is the surface, the integration over a closed surface for the magnetic flux, or for the magnetic field, for the magnetic field over a closed surface is always zero. And this is known as Gauss law for magnetic fields. And physically it means that there is no monopole for the magnetic field. There is no north only or south only. So that's Gauss law for magnetic fields. Gauss law for magnetic fields says that there can be no net magnetic flux through the surface because there can no net magnetic charge or individual magnetic dipoles enclosed by the surface. The simplest magnetic structure that can exist and thus can be enclosed by the Gaussian surface is a dipole, which consists of both source and sink for the field lines. Thus there must always be much magnetic flux into the surface as out of it. And the net magnetic flux must always be zero. So this is the Gauss law for magnetic fields. As an example for applying Gauss law for magnetic field, we see in this figure shows a closed surface along the flat top face, which has a radius 2 centimeters. A perpendicular magnetic field B of magnitude 0.3 Tesla is directed outward. And along the flat bottom, which is hidden, it's here, along the flat bottom face, a magnetic flux of 0.7 milliweber is directed outward. What are the magnitude and direction, inward or outward, of the magnetic flux through the curved surface? So according to Gauss law, the total magnetic flux on this closed surface should equal 0. So here we have the value of the magnetic field on the top surface and the radius of this top surface. So from the magnetic field and the area of this top surface, we can find out the magnetic flux from this top surface. And the bottom surface is actually, we have the magnetic flux directly. And both of them are outward. We are going to assume the outward is positive and the inward is negative. So according to Gauss law, the magnetic flux from the top surface plus the magnetic flux from the down surface plus the magnetic flux on the curved surface should equal 0, because there is no net magnetic charge. So if I know the top and the bottom and the curved is unknown and the total equals 0, I can obtain the magnetic flux as the curved one. Let us see how to do it. We say that the flux at the top equals the magnetic field at the top multiplied by the area of the top surface. So it is 0.3 Tesla multiplied by pi r squared. So it is 0.377 milliweber, and it is outward from the surface. And the bottom one is 0.7 milliweber outward. It is directly given in terms of flux. So the total flux equals the flux of the top plus the flux of the bottom plus the flux of the curved one. It should equal 0, because the integration of the total magnetic field over a closed surface, it should equal 0. Gauss law for magnetic fields, because there is no magnetic charge. Now, by applying this, we have the top one is positive, assuming the outward is positive, and the bottom one is positive, and phi curved is unknown. From this one, we can obtain the phi curved, or the flux from the curved surface, equal 1.077 with a negative signs. Negative sign would mean it would be inward the surface. It is coming inside the surface. Okay, so this is the flux on the curved surface. All right. Okay.